Greetings, fellow nerds. In this video, we're going to make a special box for general-purpose electrolysis experiments. Now, electrolysis is great for redox chemistry, as electricity is often cheaper than chemical reagents and cleaner in terms of waste products. But performing it is a hassle, as it's generally a lot slower than reagent-based chemistry, so your electrolysis cells need to be running for some time. This becomes an even bigger problem when your reaction generates toxic mists or even toxic gases, like making sulfuric acid with electrogenerated bromine, as I showed in a previous video. Now, you can leave your electrolysis cell in a fume hood like I do, but that takes up extremely valuable fume hood space for a long time that is much better spent by you doing other work that actually needs your attention. Even I don't like leaving my electrolysis cells in a fume hood. Now, you can run the reactions outside, but over long periods of time, the chance of getting bugs or other foreign materials into your cell increases substantially. The best solution is to build a custom sealed cell tailored to your chemistry, and if you're only making one thing, like say a chlorate cell, this approach is the most practical. But if you're doing lots of experiments with a great variety of electrochemical reactions, then a custom cell every time can be as impractical as using a fume hood. My approach is to use a general-purpose electrolysis box that can easily accommodate many types of electrochemistry. I got the idea when I was doing sulfuric acid by the electrobromine process and got pissed off at just how thoroughly messy and toxic the process was. The electrolysis box as shown here is a simple plastic storage box with electrical connections passing through the side, as well as a convenient DC-DC converter for regulating the voltage and current. What's most important is that it has this diaphragm pump that sucks air and any toxic gases out of the box and through an exit tube that you can exit into your fume hood or directly outside through a window. Because the gases can't escape the box except through the tube, you can conveniently place the box outside your fume hood and somewhere in your lab where it isn't in the way. The box also contains any spills or salt creepage, a particularly troublesome aspect of chlorate cells. To build the box, we start with a plastic support panel. I'm using a piece of acrylic about 2 mm in thickness. The panel is optional if you have a very strong plastic box with thick walls, so you can just attach the hardware directly to the box if you want in that case. Anyway, make sure the panel is big enough to accommodate the larger components like a diaphragm pump, the hose bar for passing the toxic gases, and the DC-DC voltage and current regulator. Now with a drill press, drill at least 2 holes for passing the bolts for electrical connections and 1 for the hose barb. You can drill more holes if you need to accommodate other hardware or if you desire stronger support. Now you can use a tap and make the appropriate threads for your bolts and hose barb. This part is optional if you intend just to use nuts to secure the bolts. Now we select our plastic storage box. These are easy to get from a department store. The plastic should be polyethylene as that's cheap and very chemically resistant while also being transparent enough to see the reactions. An acrylic box is clear but not as chemically resistant. Try and select a box that is reasonably airtight with a lid. It doesn't need to be perfectly airtight as the diaphragm pump will create a negative pressure as it pulls out the gases, so any cracks in the seal will leak inward rather than outward. Nonetheless, the tighter the seal, the better. You can always improve the seal with tape if you really need to. Once you have your box selected, drill in holes to match the positions of the holes drilled into the support plate. You can also tap the holes to create threads if desired. Now we start assembling the hardware. Here is the box and here is the support plate with the matching holes. These 4 holes are to support the diaphragm pump and are threaded so I don't need hex nuts on the other side. Okay, let me peel off the protective film here. Now we line up the support plate. First I'm going to screw in the hose barb. Looking back, I should have used a plastic hose barb for better chemical resistance, but all I had was brass at the time. I'll be sure to replace it with plastic in the future if and when this one corrodes. Now we get the power leads ready. These connect through ring connectors to bolts that will pass the power through the box. By doing it this way, we can use the same holes for support as well as power. If you prefer, you can keep them separate and pass the wires directly through a small hole. It doesn't really matter either way. Now I'm using titanium bolts for chemical resistance, but as these are expensive, you can use steel if you don't mind having to replace them if they become severely corroded. I'm tightening these with my finger for now, but I'll use a wrench later. Now we install the diaphragm pump. These are actually pretty cheap and I got mine online for about $6. Diaphragm pumps are preferred for this application because the internal metal parts are separate from the gas stream, so it can pump corrosive gases without corroding the pump. This makes them last much longer as opposed to other pumps. Now if you have a perfectly airtight box, then the pump is not strictly necessary, but I still recommend it just in case there's a crack in the seal. Okay, when that's all screwed in, we start connecting the power components. First, I'm going to set up the power regulator for the diaphragm pump. This is a small, low-power DC-DC converter and allows me to control the speed of the pump. It's currently set to 10 volts output. If you're powering your box from an already regulated power source that matches the voltage of your pump, then you don't need this part and can just connect the power directly. Now this is our main DC-DC regulator, and it features a built-in voltmeter and ammeter so we can directly monitor the voltage and current we're applying to our chemistry. I got this regulator online off eBay for about $9. We connect the power leads that are passing into the box to the output of the regulator. Now I'm connecting the input on the pump regulator to the input on the box regulator. This is because later we're going to connect external power connections that will power both regulators in parallel. Now we get some vinyl tubing and connect the hose barb of the box to the input of the pump. Now on the output side of the pump, we connect the exit tube, which is a bit of vinyl connected to a long 50-foot polyethylene tube. The tube actually leads off camera out the window of my lab. Now we install the internal connections. Here we use alligator clips attached to ring connectors with a length of wire that can reach all around the box. The ring connectors are secured using flange nuts that are also made of titanium. Finally, we tighten the nuts and bolts with wrenches. And that's all there is to the internal connections. Now, before we permanently glue the regulators to the support, we test them by connecting a power supply to the input terminals. Mine is off camera and is providing around 14 volts. Okay, let me turn it on. And there we go. The regulator is working and I can hear the pump working as well. So let's get to gluing. Here I've disconnected most of the wiring. First I'm going to glue down the regulator for the pump. I'm using marine epoxy for this purpose. Now to prevent the regulator from sliding off while the epoxy cures, I'm going to tape it down. I'll remove the tape after the epoxy hardens. Let me disconnect more of the wiring here. And now we glue down the main regulator. Looks like I don't have enough epoxy to cover the whole thing, but since this stuff is very strong, I'm not too worried. It's not handling much mechanical load. Okay, there is no need to tape down this regulator, as gravity will keep it in place. Now we let the epoxy cure overnight. Here we are the next day with everything rewired and working. I'm now setting up the electrolysis box for a test experiment. The great thing about this DC-DC regulator is that it has potentiometers to adjust the output voltage, which I'm doing here. Once I've set a maximum voltage limit to apply, in this case 3 volts, I can also set a maximum current limit by shorting out the electrodes and adjusting the other potentiometer. In this case, I'm setting a current limit of 0.1 amps or 100 milliamps. Now to set up our reaction, we just put in our beaker of electrolyte and connect up our electrodes to the appropriate alligator clips. A useful thing about a box this big is that you can also put in additional lab equipment like retort stands if you need to secure the electrodes. Anyway, put the lid on and recheck for any drift in the regular output. And we are done. We have our gas-producing electrolysis reaction safely running inside the electrolysis box. The gases are being sucked out and vented outside the lab, and I can now tuck the experiment out of the way and use my fume hood for other experiments while it runs. When it's finished, I'll return the experiment to the fume hood and open it to vent any lingering gases before observing the results. So that's it. A basic electrolysis box for safely performing gas-producing electrolytic reactions. Thanks for watching. If you would like to contribute to the continued production of science videos like this one, please support the channel on Patreon. Links are in the video description. In this video, we're going to make sulfuric acid from sulfur and water using a new process I found that I'm calling the electrobromine process.